With the bell work today, this is going back to scatter plots, correlation, all this fun stuff. And one thing I hope you guys remember, though some of you forgot, but we can correct that. Regardless of how you transform your variables, here we added 0.17, we doubled your y, we even flipped the x and the y's. But the only thing that matters is z-score, and it stays 0.28. So some of you probably were doing a lot of math that you didn't need to. Your correlation between two variables never changes, no matter how you, as long as the variables themselves are kind of just being transformed, then you're good. All right, so that is that. So here we can see what we're doing today. We're going to do part of, we're doing chapter 17. Hopefully you guys read it over the weekend, or anyways. They do things in a slightly different order in chapter 17 than what we're going to do in class. So if you read the whole thing, you've already learned about some of the stuff. Hopefully just reinforce that. I will tell you, if you didn't read it, you will probably be confused a bit at the end of class. Hopefully not too much, but you might still be confused a little bit on certain things. And I hope you go back and reread so you can kind of reinforce that knowledge. Okay. The first thing I want to do, this just bugged me from Friday. I hated that we did this example and I didn't come up with the right answer. And I figured it out how the book was intending this. And maybe you guys already had the right answer. So if you were looking at it on Friday, we looked at this problem and I just we got like 18 point something as an answer, which wasn't the right one. So I figured out how the book interprets this. It's that this 5y is just rescaling your y variable. So when you rescale a standard deviation of this, you just multiply your standard deviation. And we talked about that on some day last week, Wednesday maybe. So 5 times 3, we're going to have a new standard deviation of 15. All right, so we'll just set that aside for now. The rescaled 5y. So the mean we didn't have a problem with. That was just x minus 5y is going to be these two values, 80 minus 5 times 12, which is 20. That we didn't have any trouble with. We're going through, but it's the standard deviation here of x minus 5y. The way that they're looking at it is now the standard deviation of x, we have to add the variances and get the square root of it. The standard deviation of x is 12, so the variance is 12 squared, and we always add your variances, we're not subtracting, and now 5y has a standard deviation of 15, which means the variance is 15 squared, and that's how you get your 19.21. So the reason I don't really like this is that we don't have any context what they mean by that 5y. Are they rescaling? Are they saying we have 5y events happening? So luckily in real world problems, you don't have this ambiguity. It's very clear what the situation is. Okay, but I just wanted to correct that in case you're like, well, I don't even know how to find it now since it didn't work out. So I wanted to share something else real quick. There's nothing on this page. It says FRQ rubrics. I just wanted you guys to be aware. There's a quick thing to talk about that. There it is showing up. FRQs, when AP goes through and grades these, and this is probably not a shock to hear, there are specific rubrics that they have in mind. This is the 2019 AP test. You can find this, just search it online. You can find the actual FRQs that were used and the way that they were graded. Those of you who are doing the AP test in the spring, of course, we'll have some kind of study review session for it, but highly, highly encourage that at least at some point you kind of look through some FRQs with the rubrics, and maybe we'll do that in class. But it's just important to know that this doesn't have the question, it does have the answers for it. But there are very specific ways that these are graded. So each section is scored as either E, essentially correct, P, partially correct, I, incorrect. And the combination of those, if I scroll down a little bit, when you look at the entire FRQ, so you get a 4 if all 3 sections were essentially correct, 3 for 2 sections, well, you can read it. So based on the E's, the P's, and the I's, you get a 4, 3, 2, or 1. When I'm grading your FRQs right now, I'm not using a rubric for it. I'm going through and grading generously. Like do they have enough of some of the ideas that I can give them 2 out of 4? So I do intend to kind of veer more toward grading according to the rubric through the semester. So by December, hopefully, it's looking more like I'm grading from the rubric. Again, not too much to say about that, but I thought it was worth going over for a second for you guys to know that there are rubrics that, again, just to go back, to refer back to it, it's good to know that there are FRQs you can go through and you can figure out what a good answer would look like. Okay, finished talking about that. Now we can look at some other stuff. The very first part of chapter 17, we're introduced to Bernoulli trials. All right, we'll talk about that in a second, but Bernoulli trials have 3 characteristics. The outcomes must be binary, so the failure or success are the only options. Independent, so each trial must be independent and there must be the same probability for each trial. And those are Bernoulli trials. And they're named after Daniel Bernoulli. So if you can identify, first of all, that these are Bernoulli trials, like flipping a coin over and over again. It's binary. It's either heads or tails. It's independent. What happens on one doesn't affect the other. And every single time there's a 50% chance of success, whatever you define success to be. So that's a great example of Bernoulli trial. And once you know that, you can do certain kinds of analysis on it. And we're going to do 2 of them in this chapter. If you already read through, you're familiar with the binomial probability and geometric probability. So that we're not going to look at geometric today. So that's why we're going a little bit out of order. That's the very first thing chapter 17 talks about. Okay. There we go. So we're going to definitely come back to this idea of Bernoulli trials, and the outcomes must be binary, independent, and the same probability for each trial. So for now, we're just going to leave it at that. Bernoulli trials. Okay, now let's jump into this. In the 2005 Conference USA basketball tournament, Memphis trailed Louisville by 2 points. At the buzzer, Memphis's Darius Washington attempted a 3-pointer. He missed but was fouled and went to the line for 3 free throws. Each free throw is worth 1 point. Was it smart to foul? And this is a general question. Yes, it was smart.
It was smart.
Okay.
Wait. No, wait. I say no.
I mean, it depends on like how good he is at shooting free throws.
Okay, there we go. There's more to the story, right? There's a big maybe on this. So we should find out maybe some more information. So there we are.
That's also a good idea.
Okay. So before we jump into some more information that we need, let's kind of look at this. What are all the possible ways that, not the 3-point shot, what are the possible ways that the free throws could fall?
0.5 for each.
Well, and we'll get to the probabilities of that in a second.
Oh, you mean like all 3 make?
Right, there you go. And I'm going to use pluses for make and minus for miss, just so I don't have to write out anything. So all 3 made. What's another outcome?
All 3 miss.
All 3 miss. What else we got?
He makes the first 2 and misses the last one.
All right, you can keep shouting out other combinations here.
He misses the first one and makes the last 2.
Misses the first and last, but makes the second.
Wait, misses first and last, but makes the second. Got it.
Makes the first and last and misses the second.
Okay. Yeah, there's
Is the make miss miss, is that part already answered?
no, that one is not there yet.
Yeah, you can put that one in.
There we go.
Miss, make. Oh wait, that's
Yep.
there.
Yeah. Close though.
Miss, make.
There it is. Miss, make. Okay, and now this is, it's binary. We said this from the beginning. These are Bernoulli trials, I should tell you. It's binary, meaning there's only 2 outcomes. We've got 3 of these trials, so we know there's going to be 8 outcomes. 2 cubed. So if there were 4 trials, if he had 4 shots that we were looking at, then we could just do 2 to the 4th power. So we've got our 8 possible outcomes on this. Okay, and this right here isn't something you need to worry about too much. It can be helpful. We'll see in a second. But there we go. So we're going to look into this a little bit more. Now, I should add right at the beginning, this is a real event, and we're going to get to see how this turned out through the power of movies. All right, so I'm just going to copy this down. It'll be really fun to watch me do this for a second. There it is. So those are the outcomes that we've got. I'll now erase them from the bottom so we can write there. And again, we've got 8 outcomes. Okay. So there we are. So we're now going to figure out the probability that Memphis will win, lose, or go to overtime. All right. And it's important to, well, I mean, it said in the context at the beginning that they were down by 2 points. Specifically, the score was 75 to 73. So what are the, before we worry about all this stuff up at the top, let's just jump down here and we need to figure out what's the probability that, what are the conditions that are met and required in order to win there? Does that make sense? What's needed in order to win?
Makes all the free throws.
All right, make 3. What's required? I'm going to jump over to overtime. What's required for overtime?
Make 2.
There we are. Which means losing is
One.
or
0.
0. So making 0 or 1 right there. So now we can figure out the probability, knowing we have a new piece of information, 72% free throw shooter. Knowing that he makes 72% of his free throws, we can figure out the probability of making 3. All right. It's a probability of what?
Make.
Make and make and make. All right, that's a plus and a plus and a plus. I'm not going to spend long on this. We know the probability of making it is 0.72. So 0.72 times itself 3 times. So I'll just put cubed. All right, we're not going to spend long on these basic probability calculations. And go ahead and write in what that probability is. Okay, there it is, 0.373, very good. I'm going to jump over to overtime again. The probability that we're calculating here is what?
making 2 and missing 1.
Make and miss. You guys should be able to find that. I'll just put the equals there. Someone can write what that is. Awesome. 0.145. Of course, it goes on from there, but if you leave it at 3 decimals, that should be okay for us. Now, making 0, making 1. Let's start with making 1. What's the probability we're doing there?
Missing 2 and making 1.
There you go. And I'm sure you guys were already calculating that, so I'll just put that right there. And of course, we can see the other thing here. We have to calculate 2 probabilities. Probability of missing all 3. So you guys could put what those probabilities are. All right. Good all around. Now, if you add this up, this does not add up to 100%. All right, let's figure out why it does not. So with previous probability problems, we're dealing with, well, we've got 3 events happening here, right? Make, like in the first one. But that make is how many outcomes up here end with 3 makes?
1.
1. So we've got 1 outcome. So really what I'm doing here is I'm going to take this probability and multiply it by 1. All right, no difference, 0.373. So it looks like that's the probability they could win. But we have to be careful about some of these other things. I'm going to jump over to overtime again. And overtime is where they make 2, miss 1. So how many outcomes have making 2 and missing 1?
3.
3 of them. All right, so I can see that these 2 right here and this one right here all end with 2 makes and 1 miss. Now, each one of these has a probability of 0.145 happening. So if I've got, and that 2 means 2 makes that I wrote beside it. So if there are 3 outcomes with 2 makes, then I need to show that this is 3 different, and it's important to recognize these are mutually exclusive events. Make, miss is mutually exclusive with make, miss, make. But they have the same probability of happening, so I can just add those up. And what is our probability going to be?
Point 0.435.
There it is, 0.435. I'll put a box around that one. And probability of overtime is about 43.5%. All right, now we can move over to lose. We've got 2 different outcomes, or 2 different situations, and how many times could we get just 1 made?
3.
3. There we are. So those are 1 make, and of course we can see the last one here is 0 makes. So the probability of 0 right here, we just need to multiply by 1 because there's only 1 outcome with that. But now the probability of 1 make, sorry, we need to multiply by 3. All right, so 0.056 times 3 is what?
.168.
There it is. Okay, and these are also mutually exclusive. So what I was essentially doing is I was taking all 4 of these outcomes up at the top right here that are 0 and 1, and I'm adding those 4 probabilities together. So 0.056 plus 0.056 plus 0.056 plus 0.022, those are all mutually exclusive events. So I can just add them up and we get our 0.190. Now again, if you look at this, this doesn't quite add up to 100%. That's just because of rounding. But we've got our probability of a tie. We've got our probability of a loss. And we've got our probability of a win. All right. So this is dealing with Bernoulli trials right here. And we can see that there's a different method we need to go through in order to get these probabilities. But we will figure out a formula for this a little later on. But notice again, your 1, 3, 3, 1 breakdown. Now that 1, 3, 3, 1 might sound familiar if you're thinking of your trinomials. But anyways, that 1, 3, 3, 1, if you add it up, there's 8. And so there's your 8 outcomes, 2 to the 3rd power. If we add another, it would break down like this: 1, 4, 6, 4, 1, and that's going to be that's going to add up to 16. So you can see what's going on. So it's just polynomial expansion going on. All right, fun times. Get some algebra 2 thrown in there just for good measure.
Mr. Davis?
Yeah.
Those percentages don't add up to 1. 0.3.
Is it close though?
It's 0.998.
Right. That's from our rounding errors, because honestly, this 0.435 should, I believe, be 0.436. And maybe this should be a 0.191 when we add it up,
okay.
if we did better rounding.
Gotcha.
So yeah, that's truncation errors. Yeah, I'm glad you checked. And it would be preferable to have everything exactly right. So let's kind of see what's going on here. We have different, I'm going to create some space. We've got different notation here. This is actually probably going to be something new. I want to erase or not? Okay, it's just going slow, sorry. So our notation here, you see this NCK, and really it should be subscript. NCK, the way we say this is N choose K. And N right here is, we're just going to think of it as our number of trials. And K is going to be our number of successes. All right, number of successes. So if we're, in this case, if we have 3 trials, 3 free throw shots, and we're going to choose, now number of successes, if we're talking about overtime, that's 2 successes, making 2 of them. So 3 choose 2. This is not that hard to do. 3 choose 2. We just did that right over here, right? And it's not that big of a deal. But it gets way more difficult if we have a lot of trials. And so just as an example, why don't you do, I'll show you how to do this on the calculator. But we're going to figure out, what if we had 10 free throws and we wanted to know the probability that he made half of them? Sorry, I'm jumping ahead. Not the probability that he makes half of them, but if there are 10 trials, how many combinations are there that he could shoot to end up with 5 successes? So this is going to be an integer number, the number of trials that will end in 5 successes if you shoot 10 free throws. Or the number of possible ways. Got to get this straight. So anyways, the way we can do this on the calculator is you actually have this in choose k function. Of course, on the calculator it says NCR, and I'll show you where to find that. But what I'm going to want to do is I'm going to put, let's say there are 10 trials, 10 free throw shots. The number of possible ways that you could end up with 5 successes, which is not the same as the probability, is going to be 10 in choose R, and then 5 will be our R value, or K. I don't know why the calculator calls it R. So to get there, you want to first of all, on your main screen on your calculator, if you can see that, just put 10 down, because you need to have your trials down first. So 10 is your number of trials. And then, if you can follow this, you want to go to math and probability. And then you'll see NCR, which is your third choice. So if there are 10 trials and you want to find the number of paths to getting 250, sorry, to get 5 successes out of 10 trials, I just said it, there's 252 paths to get there. And I'll show you what that means, because when I say there are 252 paths, I think it's more clearly shown if we look at Pascal's triangle. But is everyone good with this? Was everyone able to find the NCR on their calculator? Okay. If you got confused on that, let me know, because you're going to need to calculate this. And I'll also add right here, we're going to be learning a formula and using a formula that later the calculator will do for us. But for today, we're going to do it by hand. Not this really long way that we're doing right now, but a slightly faster way. All right, let me clear all this out of the way. And the first thing I wanted to mention on this, it is Pascal's triangle. And it has this weird notation of in K. So this is the same as in choose K, but they write it like this. So like this one right here would be, actually, let me go to the previous example we used. We used 3 choose 2, 3 choose 2. Well, there it is. That's the same as 3 choose 2, like that. And if you go over here to the equivalent spot, the answer is 3. So Pascal's triangle is really just a collection of all the choose function. And you can see this is your 0 row. Here's your 1 row. These are all 2s, 3s. And then as you go across, you count 0, 1, 2, 3, 4. So when you get down to this one right here, that's 5 choose 2. And that's going to be equivalent to this one right here. Okay, and now, and you can double check that on your calculator. You could do 5 NCR 2, and you'll get 10 as your answer. All right, and I just wanted to kind of show you what I mean by the number of paths. And we looked at this before when we looked at the normal distribution. But what you've got here is, let's say it is this 10, 5 choose 2. We want to find the number of possible ways of combining successes and failures to end at this particular spot. So I'm going to say every time I go left is a failure. Every time I go right is a success. So I could have 1, 2, 3 failures in a row and then 2 successes. I could have 2 successes in a row, then 3 failures. I could have a failure, 2 successes, and then 2 failures. I could do 2 failures, 2 successes, 1 failure, and so on. 1 success, 3 failures, 1 success. And I'm not going to go through all 10, but there are 10 possible paths that I can follow to get to 10, that 10 right there. And so if you kind of, I don't know if it's helpful to help you think of what choose is referring to, but that's kind of one way of thinking about it. And it doesn't take long if you want to try not even a crazy number, like 20 choose 12. You can see how fast this grows. So I'll just do that real quick. 20 choose 12. I just picked random stuff here. And I hit the wrong button, of course. And we can see that's over 125,000 paths. So there we go. We're not going to calculate this by hand. All right. So now we're going to jump back to this, and we're going to actually calculate binomial probability. There we go. I can talk. So we want to figure out that we're going back to the basketball example. We've already calculated this probability, but we're going to now derive a formula that we can use to do this. The probability of overtime requires how many successes?
Two.
There you go, 2. And when it says the probability of success, it's not the probability of overtime. What's the probability of one success?
Zero point 0.72, right?
That's right. Yeah. And yeah, if you if you forgot the number, that's okay. So 0.72 was the free throw percent. So that's what we've got here, which means the probability of failure is a complement. I'll just write it down, 0.28. So from the get-go, we want to establish that these are Bernoulli trials. So is it binary? I think it's fair to say it's binary. You either make the shot or you miss it. So binary, yes. Is it independent? I think it's fair to say, to assume in this case, that whether you make the previous shot or not shouldn't affect whether you can make the second one if you're a natural 72% free throw shooter. So yes, it's independent. And do you have the same probability each time? I think it's fair if you've shot enough free throws, let's say that 72% is your true shooting average, then yeah, we can assume every single time you got the same probability of making it. So it meets all those criteria. So what we essentially did, here was our actual calculation. What we did was the 3 times that you could end with 2 successes times 0.72 times 0.72 times 0.28. So that was the actual calculation, and it got us whatever that number was. What was probability of a tie? I forget. 0.435? Okay. So what we're going to do is turn this into a formula. And this 3, we just spent time talking about, that's really 3 choose 2. And when you have 3 choose 2, it ends with this number 3. All right, but really it was 3 choose 2. And this next one, we can see it says 0.72 raised to the power of 2. Now 2 happens to be the number of successes. So it's this number right here. So it's raised to the power of the number of successes, and then multiplied by failure probability times whatever's left over, raised to the power of whatever's left over. There were 3 trials, 2 of them were successes, so 1 of them's a failure, so I raised it to that power. And of course, this is still the same thing. I haven't fundamentally changed the problem. It's still 0.435. Okay, so now we can generalize this formula even further and get this right here. So if I added this right here, the probability that a random variable x equaled 2 successes, it was that right there. And yeah, the only difference is they use this notation for n choose k. But there it is. It's the number of paths. So maybe I could say number of outcomes right here. The n choose k is going to be the number of outcomes. And then the p to the power of k is going to be, well, p is the probability of success. And k is number of successes okay. And the only other thing is K right here is the number of trials. So with 3 numbers, you can figure out the probability of this happening. You need to know the number of trials, you need to know the number of successes, and the probability of success. With that, you're good. Those of you who have already read, just to clarify right now, they give you a slightly different formula. It's really the same thing. Theirs, actually, I'm not looking at it, so is slightly different. It's going to be N choose K times P to the power of K times Q to the power of N minus K. I think that's how they have it written. And Q is the probability of failure. I don't like it that way as much because, first of all, it adds another variable, Q. So I like to keep it as 1 minus P, the probability of failure. But Q, if you like it that way, just keep in mind Q is the probability of failure. Okay, and also just keep in mind that these 2 exponents, when you add them up, have to add up to N. So that will sum up to N. Okay, and then I know it's just looking at a formula right now, not super exciting. We're going to go through some practice problems with it. And we'll do that, I guess, a little later, doing things a bit out of order. But we're going to actually now wrap this activity up to figure out what happened in real life when Memphis got these 3 free throws. We know from the calculations we've done that it's a 0.373 probability that they win, 0.190 essentially, and then 0.435 with some slightly off probabilities. Okay, so let's watch the shots. All right. Is the video going to show up? There it is. So here's the actual foul. It's going to be a little bit choppy, but hopefully you can get enough of the setting. All right, so he got fouled. Again, a little choppy, but hopefully you can hear the Okay, so here's the first free throw.
For the season, 72%. If he hits 3 in a row, Memphis goes to the NCAA championship. 2 to go. Boy, we've got to take the pressure off right now.
Okay, made the first one. And actually, before we look at the second shot, let's go back to our presentation, to the table we were filling in. Okay, let me make it big. So now after this, he made the first one. We're good with that. Now the score is 75-74. Probability that, let's recalculate the probabilities, just some good practice with this. What does he need to do in order to, what does he need to make in order to win?
3 of them.
All right, well, he's already made 1. So now we're jumping to, there's 2 shots left.
2 more.
There you go. So the probability of a make and a make I'll just put this right here. You guys can write that number in. Probability, what does he have to do to lose?
Miss 1 or 2.
Well, he would need to miss both of them in order to lose. Yeah. He's got 2 shots. He only needs to make 1. So therefore, the and then to tie would be making and missing. Okay, so the only other thing to consider with this is how many paths are there to victory? How many ways, with 2 shots, how many ways are there?
One.
1, yeah, there's make. I'll just put all the possibilities up here. How many paths are there to defeat, to loss?
Uno.
There you go. So there's victory, there's loss. That means we've got 2 paths to, if I can get it, 2 paths to tying, making the first, making the second, and missing the other, or meaning either making the first or the second, but not the other. So there we go. We can double that. So 0.404, something like that. So we're in the ballpark. That should be good for our probability. Okay, just some good probability practice. Let's look now at this one more time. Well, actually, we'll watch both. No, we won't. What's going on here? We'll watch the second shot. Uh-oh. Okay, so he missed the second shot. Let me get the last one queued up. Okay. All right. Taking a sweet time. All right, so now we know that he missed with that shot. So now we're just going to calculate this one last time. 74 to 75 is the score. There's 1 shot left. Can he win?
No.
No. What is the probability that he loses?
Point 5.
0.28.
Oh, my bad. Yeah.
There it is. It's a 0.28. So now it comes down to 1 shot, and maybe it's not fair to say the probability that he loses, but his team loses. That's got to be a lot of pressure. So there we go. Now we come down to this. Still looking good. Did he pull it out? Let's see. Last. I know you guys are just biting your nails trying to figure out what happened 15 years ago.
I will be hard pressed to tell you right now that you'll see a more pressurized situation this year. Tournament's on the line. Louisville wins. Somebody's got to go help that kid out. And the first man there is Joe.
Oh, you know, it's sad for him, but I bet it brings him a little bit of comfort knowing that his struggles made for a great statistics problem. So that, I'm sure, is consolation enough. All right, so they lost. Let's move ahead now. Okay, now this is the binomial distribution. Maybe this is slightly out of order, but we're all going to tie it back together. So the binomial distribution is an actual distribution. Think of it like a histogram. It's basically what it is. And it depends on 2 numbers to figure out what the distribution is going to be, is the number of trials and the probability of success. And we're using lowercase p for probability, though that lowercase p is also used for population proportion, but we won't worry about that right now. So this is just a way of showing the binomial distribution. And now I can put in the N and the P. So just to look at our scenario again, there were 3 free throws with a 0.72 probability of success on each trial. And here is the distribution. This might not look like much right now. It does look, I don't know, how would you describe that distribution?
Skewed to the left.
Skewed to the left, I agree. How many modes does it have?
Uno.
Uno. Okay, so unimodal, skewed left. All right, we're happy with that. So, but now we can kind of go and we can see if these probabilities match up. So the probability, this does it for us on the, and it can tell us the probability of 3 successes is 0.373. Well, that number seems familiar. We already calculated that. So 37% right there. Probability of 2, this would be the probability of a tie, 0.4355. So there we are. We can see that we've got the same number calculated right here. And then now here we don't want exactly 1 success. We were going to figure out if it's either 0 or 1. I can put my numbers in, right? And that's 19.1%. So we had 1.190. So you can see there's some rounding going on. So a binomial distribution here can be used almost like a normal distribution. If we consider this like your percentile score, and this is a normal CDF calculation that said, okay, from 0 to 1, what's the probability of the area under the curve here? So we're tying this back into our chapter 6 normal distributions in a certain way. So what I want to do before we move away from this is I'm going to give you guys some other examples, and I want to see if you guys can tell me what my N and P should be. So the next example is I'm going to flip a coin 4 times, and I want to know how many heads I can get.
N would be 4, right?
That's right.
P is 0.5.
0.5, there we go. There's a distribution. And so now if you wanted to know, okay, I'm going to flip the coin 4 times, how likely am I to get just 1 success, whether you call that heads or tails? So if I want to get just 1 success, looks like I have a probability here of 0.25. Now, maybe just for whatever reason in your scenario, you want to know getting anywhere from 0 to 3 successes. So anything except all 4 tails or heads or whatever success is. And now you can see it's a 0.9375 probability. All right, so, and we're going to do calculations like this, but not using this applet. Last example, let's say that you are running a gambling game. All right, and let's say you allow someone 12 rolls of a die, and they just have to get a 6 3 times out of 12 rolls. Is that a good bet? How do we figure that out?
First, you're going to put N as 12.
12 trials.
And you're going to put 0.25 as your P. Wait, no. I'll let someone else do that one. I don't know.
All right. So 12 rolls and you have to get a 6 3 times. So what's the probability of success?
Would you cube the probability? No.
No,
Okay.
no, we're just like that for a single trial, what's the probability of succeeding?
Oh,
0.16 or 0.17.
Right. I'll just put the 6. It's 1/6 in case you're stumped out there. So 1 in 6 probability that you're going to get a 6. So each trial, there's a 1 in 6 probability you're going to succeed. Here's the distribution of that. And you have to get at least 3 successes in order to win this gambling game. So I'm going to figure out the probability going from 3 all the way to 12. If you get 12 successes, then you win the same. And I don't know what you're expecting. There's only a 32% chance that's going to happen. So if you are in the business of cheating people out of their money, then I just introduced a new way for you guys to do that. So there you are. Now we've got, now if we go all the way up to 15 trials, so if you let someone roll 15 times and they just needed 3 6s, you still have less than 50% chance of winning that game. So maybe it's a little bit counterintuitive. You'd think if you had 15 rolls, getting 3 6s, that shouldn't be hard to do. You did it less than half the time. Okay, so maybe enough about that, but the distribution you can see well, maybe we can look at this at the very end. We talked about one being unimodal and skewed. How would you describe this one? Any thoughts on the shape of this distribution?
I'd say slightly skewed to the right.
Yeah. And we're going to talk more about that tomorrow. But for now, it's just suffices to say, it looks kind of skewed. It looks mostly normal, but maybe not fully. All right. Let me get back to this. All right. So, and this is kind of the takeaway. The binomial distribution is unimodal, but not necessarily approximately normal, and that's something we're going to get into more. All right, so the binomial setting. Now we jump into the last, I think this is the last little bit that we need to talk about before we can do some practice and call it a day. So to determine if a situation is appropriate for using that binomial formula that we just wrote down, the one that looked kind of complicated, to determine if that's even an appropriate thing to do, we need to meet 4 criteria. 3 of them we already know. The outcomes must be binary. They must be independent. Here's the other one. There must be a limited number of trials. So you're always on the lookout for this right here. If you've already read the chapter, you know there's a difference between this and the geometric probability. And if it's a limited number of trials, then you're talking about binomial probability every time. All right. And then the last one is the same probability for each trial. So of course our acronym here is BINS. So BINS is, and we're going to kind of run through this with a few examples. Now, as far as these two, independent and same probability, just to touch on those a little bit more, 2 trials can be independent without having the same probability. Like flipping a coin, then rolling a die, and then flipping a coin and rolling a die, flipping a coin, rolling a die, back and forth. Yes, they're all independent. One doesn't affect the other, but you go from a 0.5 probability of success here to a 0.17 probability here. And you just alternate back and forth. So in that case, this would not work for a binomial calculation. All right. So I will maybe stop right here for a second and make sure you guys have time to copy this down, the BINS and just whatever shorthand you want to use for binary, independent, limited number of trials, same probability. Okay, so we're going to look at a few examples. The only thing we're doing for the first couple is figuring out if the binomial setting criteria have been met. All right, so shuffle a deck of cards, turn over the top card, put the card back in the deck and shuffle again. Repeat this process 10 times. Let random variable X equal the number of aces you observe. All right. So I'm going to use Ben's as my checklist here. I'm going to start at the top. Is it binary?
Yes.
Yes, it is. What is the success here?
Getting an ace.
Ace. What is a failure?
Not getting an ace.
Not getting an ace. Okay. Independent. Yes or no?
Yes.
Yes, it is. Looks like there's replacement. So every card has the same probability of being drawn on any given turn, any given time we do this. In, do we have a limited number of trials?
Yes.
All right, n equals what?
10.
10. And, oh, I put a check mark there. Is it the same probability each time?
Yeah.
All right, it is. And what is the probability?
Is it 1/13? Wait.
There it is. 1/13. Of course, there are 4 aces in a deck of 52. So yeah, 1 in 13. All right. So very good. Hopefully we're good with that. What else was I going to say? Oh yeah. So we're not actually asking for a probability calculation right now. There's no question here that says, oh, what's the probability of this happening? We've got a situation set up, so we're prepared and we're set up ready to go for a probability question. So now I could say, what's the probability of getting 6 successes out of this? And we could calculate that. We will do an example. So maybe this would be my question that I would ask. But right now there's not a question. Okay. Next one. We're going to choose 5 students at random from the class. Let y equal the number of students who are over 6 feet tall. Is this binary?
Yes.
Okay. This one can cause some more problems. In the last one, we were dealing with categorical variable, ace or not an ace. So it's pretty easy. Here, it's quantitative, your height, but it's still binary in the sense you're over 6 feet tall or you're not, success or fail. So yes, this is success is over 6 feet, which means failure would be, I guess, right at 6 feet would be considered a failure. So, so less than or equal to 6 feet. All right, independent.
I don't think it would be.
Okay, why not?
Because the number of students who are over 6 feet tall, like the probability of choosing a student who is over 6 feet tall goes up or down depending on the number of students you choose that are not over 6 feet tall.
Okay, there you go. Okay, and that's you said it. So, oh, sorry, I put a check mark. It's not. That's an X. So maybe the wording here is a little bit vague, and the wording could be improved. But assuming what they mean is, I'm going to pick a student, and they're going to be part of the group, part of the sample. I'm going to pick another student, they're going to be part of the sample. And we can't pick the same person 5 times in a row. Assuming that there's no replacement, then yeah, the probability is changing. So just like you were saying, if we pick a few people over 6 feet tall, then the probability is going to change for that being selected. And in fact, I'll just jump down to the last one here. That means it's not the same probability. So probability changes. All right, so we can't use our formula for this. I couldn't ask you for the probability of exactly 3 being over 6 feet tall because it doesn't meet these criteria. You can't do that calculation. But, just to finish this off, does it have a set number of trials?
Yes.
Okay, and in here is there. I'll just do it. N is 5. There are 5 students, so it does have a set number of trials. That's actually, it seems kind of simple here, but like I said, that's going to be very, very important after on Wednesday when we start looking at the geometric probability of something happening. So you have to look for that set number of trials in order to know it's binomial. Okay. We got it. This example here. Pedro drives the same route to work on Monday through Friday. His route includes 1 traffic light. According to the local traffic department, there is a 55% chance that the light will be red on a randomly selected workday. Suppose we choose 10 of Pedro's workdays at random and let y equal the number of times the light is red. Explain why y is a binomial random variable. So they're not even saying is it, they're telling us it is. But regardless, we're still looking at this. Why is it binary?
Because it can either be red or not.
There you go. So it can be success. In this case, success is red and failure is not red. Of course, opposite of how we normally consider success or failure, but for probability's sake, a red is a success. Independent.
Yes.
Yeah, you can just say something to the effect, yeah, each day has the same probability. N, limited number of trials.
Yes.
All right, in here is 10 days. And finally, same probability each day.
Yes.
Yeah, so in our probability, here's 0.55. Going back to independent, what I should have said is whether you get red or green or yellow one day doesn't affect whether you're going to get red or green the next day. So it is independent. And now we can do this. We're going to now find the probability that the light is red on exactly 7 days. And I just need to reiterate here, we can only do this calculation because we've confirmed that it meets these criteria. So now we're saying, okay, it's good. We're good to go. Let me remind you of that formula, which is the probability that x equals a specific number of successes is going to be in choose k times the probability of success raised to the power of k times the probability of failure raised to the power of number of failures, which is n minus k. So let's start plugging stuff in. What is this going to look like when we plug numbers in? Well, let me say this. We already have our N and our P right here. You can see it in this box. What's our K going to be?
7.
7. Okay. So just to kind of run through this, we're going to be taking this N, K, and P, and anywhere there's an N, K, or P, we're going to put it in the right spot. So it's going to be 10, choose 7, times 0.55 raised to the power of 7 times 0.45, that's the complement, that's the probability of failure, to the power of 3. And notice that the two exponents have to add up to n. 7 plus 3 is 10. So that's what I can do on the calculator. If you forgot how to do the choose on your calculator, I can remind you of that. And I'm going to go ahead and put my answer down. Actually, no, I'm not. You're going to write your answer down as soon as you get it. Someone will. All right. 0.166, it carries on, so however far you want to show up, but 0.66 is good. I'm going to show that point there. There it is. So hopefully you guys were able to go through and understand this calculation. Tomorrow, I'm going to show you almost first thing how to do this even easier than that, where you don't even have to plug these numbers into the formula. But I think it's worth doing this a few times just to make sure that's really making sense. And there's not much in your homework tonight. So a lot of your homework, assuming it's okay to move ahead. Does anyone have any questions before I do that? Okay. So is there anything else? Oh yeah, I forgot this is in there twice. So this right here, actually I'm not sure that we're gonna go through it. I'll just do 2 of them real quick. But this is an example from your textbook. You're gonna have a problem like this. And you're just determining, are these Bernoulli trials? Remember chapter 17, we have different kinds of probability analyses going on. So probability calculations. So we're only looking at, does this meet the Bernoulli trial criteria? Are they binary, independent, and same probability each time? So let's just look at A real quick and try and answer that. You're rolling 5 dice and you need to get at least 2 6s to win the game. Is it binary?
Yeah.
Okay, what is a success?
2 6s.
Well, we're talking about success in each individual event.
Oh, 1 6.
Yeah, so getting a 6 is a success. Not getting a 6, so 1 through 5 is failure. So actually, I really should just say not 6 right there. But anyways, it's binary. Is it independent?
Yes.
Yeah. Dice don't affect each other. And is it the same probability?
Yes.
Yeah. And what is the probability?
1 6.
There it is. Okay. So it meets those. That would be Bernoulli trials. We could do all kinds of different problems with it based on what they're asking. All right. And the other one we'll look through is D right here. A city council of 11 Republicans and 8 Democrats pick a committee of 4 at random. What's the probability they choose all Democrats? Now, we're not answering that question. We're trying to figure out, is it binary, independent, and same probability? Is it binary?
Yeah.
Yeah. And here we know that a success for this problem, the way they're asking it, would be a Democrat. Failure would be a Republican. They're asking for all Democrats. So that's where we get that. Independent. Are these independent?
No.
No.
No. All right. Once you're picked for the committee, you can't be picked again. So the first person who's picked will affect the probability of the next person who's picked. So there it is. That means it's not the same probability. We can move ahead. Hopefully that's clear. Everyone's feeling good about it. Okay, we are going to look at this one. This one has a little more subtlety in it. Department of Transportation report about air travel found that airlines misplace about 5 bags per 1,000 passengers. So you're traveling with a group of people who have checked 22 pieces of luggage on your flight. Can you consider the fate of these bags to be Bernoulli trials? What do we think? Or, well, and let's just do it one at a time, sorry, but binary, what do we think?
Yeah.
Okay, and success is?
Not getting your baggage.
Sure, if we want to define it that way, not getting luggage. If I can, it's the end of the day, so I can barely talk. That means failure is getting luggage. All right, independent.
Yeah.
Okay. And this is where it's a little bit more subtle. So, and I understand if like, this is kind of weird the first time you see it, but hopefully just as one example can make you think about it. So yeah, it's 5 bags per 1,000 passengers on average, but it might be fair to say that if a plane is missing any luggage, it's more likely to be missing quite a bit of luggage. So it might not be independent, and maybe if like one person in the group is missing luggage, there's a better chance that someone else in the group is missing luggage. I don't know if that's true, but I think it's fair to consider it maybe not independent. Now, if you disagree with my logic, you can justify it yourself, but we don't need to spend time on that right now. I want to get you guys off to enjoy the rest of your stats-filled day, because I know that's what you're going to be thinking about. Okay, I just wanted to go through this one. Now we can just do one quick example. I don't even think I'm not going to even solve for the final answer. Just wanted to kind of set it up. We're only looking at this. There's a lot of problems in this chapter that we haven't talked about the content yet, so you can't really answer it. So assuming that our binomial setting has been met and bins is all good, we've got an archer, and you can't see it from here, but the archer has a probability of hitting a bullseye at 0.8. This is a, sorry about that. Let me erase real quick. All right, my hand hits the screen and screws it up. So probability of 80% chance of hitting the bullseye because this is an Olympic archer. All right, so now we need to use this formula. The probability of, it says 8 bullseyes. So x equals 8 is gonna be n choose k of p to the power of k times 1 minus p to the power of n minus k. So what is n for this problem?
Ten.
10. And k is
8.
8. So as long as we know these 3 numbers, we can plug this into our calculation. And I'll just repeat for the last time, you're not gonna have to do this formula by hand very much, maybe if at all after today, but it's worth it for just now. So 10, choose 8 times 0.8 to the power of 8 times 0.2, which is the complement, to the power of whatever's left over, which is 2. That is something you guys can plug into your calculator, come up with the answer. I'm going to call that good. I just wanted you guys to see the formula one more time. So if there are any questions, you can hang out and ask those. There's your homework. Make sure you read chapter 17 if you haven't. And like I said at the beginning, it might be a little bit confusing at the end of the day. Hopefully not. But if you reread this, it'll help reinforce some of these ideas. Not much homework. So anyways, that's all I've got for today. Have a wonderful day, and I'll see you tomorrow.